Be the second lecture over carbohydrates, so the chapter 23. So this will be the last lecture over this chapter. So in the first lecture, we talked about the monosaccharides, right, the simple sugars, and in this lecture, we'll talk about the oligosaccharides. So they're usually 2 to 10 carbohydrates attached to each other, or the polysaccharides, which are polymers of 10 to hundreds of carbohydrates linked together. Okay, so if we take 2 carbohydrates, and if we look at the hemiacetal carbon on 1, and so this would be carbon 1, right? And on the other carbohydrate, so that's carbon 1, 2, 3, and 4. And so 2 alcohols can react with each other. And in this case, we're going to make an acetal. So if we lose a molecule of water, right, so H, OH, and then if we attach this oxygen here, so lose the water, condensation, and make this bond, and then now that's an acetal, right? So that's an acetal at this carbon, because it has a carbon with 2 OR groups attached. And at this carbon, it's just an ether. So in organic chemistry, we would call this an acetal. In carbohydrate chemistry, that's called a glycosidic linkage. Okay, so that would form then, if you take these two monosaccharides and you link them together, then you would make a disaccharide. So here's a few examples of disaccharides. So we'll use this to cover some of the nomenclature of these disaccharides. So this one's called maltose. So maltose is a disaccharide of 2 glucose molecules, basically. So the terminology, so this is referring to this carbohydrate, this is referring to this carbohydrate. Well, this is the carbohydrate that has the free hemiacetal end. So that's going to be the one that's last in the name. Okay, so if we go through the name, so why is this alpha? So this was the oxygen that would have been the OH if it was a monosaccharide, and that's trans to the CH2OH, so that's alpha, right? If you remember, if the OH at the hemiacetal carbon and the CH2OH are cis, then it's beta. If it's trans, then it's alpha. It's D. How do we know it's D? So you remember, if we draw the Hallworth projection, the CH2OH in the Hallworth, if it's drawn up, then it's a D sugar. Or if it's a D sugar, we draw the CH2OH up. So this 1,4, what does that mean? So that means on this carbohydrate, it's that carbon number 1 where the linkage occurs at, and then 1, 2, 3, 4 on this carbohydrate, that linkage is at carbon number 4. So it's a 1,4 glycosidic bond. And then beta, because this OH at the hemiacetal carbon and the CH2OH are cis to each other, so that's beta. And D, again, because the CH2OH is drawn up in the Hallworth projection, that would have been, it's a D sugar. And pyranose, because this is a 6-member ring, right? As opposed to the furanose, which would have been a 5-member ring. So this is sucrose, so this is table sugar. So if you're sweetening your tea or throwing a little sugar on your cereal, then you're putting sucrose on it. And so again, if we go through the nomenclature, so alpha, because this, so that's the hemiacetal carbon that would have been the hemiacetal carbon on that carbon, that's now the acetal carbon. And that oxygen is trans to the CH2OH, so it's alpha. D, again, the CH2OH is drawn up, so that's what you would do if it was a D sugar. 1,2 linkage, so on this carbon, so on this carbohydrate, that's carbon number 1, and on this carbohydrate, that's carbon 1, and that's carbon number 2. So the linkage is between carbon 1 of one sugar and carbon 2 of the other sugar. Okay, and then beta, because this is at the hemiacetal carbon, or hemiketal carbon is cis to the CH2OH, so it's beta, and D, right, again the CH2OH is up, so we know that that was from a D sugar. So that's one thing that you should understand with disaccharides is given a disaccharides, be able to classify the glycosidic bond as 1,2, 1,4, for example, and is it an alpha or a beta linkage? All right, so this is a beta linkage. Right, so both of these are, what happened? Both of these are beta, right? Because this is cis to that, and this is cis to that, so they're both beta. Oh, so this one's lactose. So you probably heard of lactose before. If some people are lactose intolerant, so they can't drink milk or ice cream unless they have milk or ice cream that's lactose free. So you find about 2 to 8% of milk by weight is lactose. And then of course you can have higher order oligosaccharides, so more than two carbohydrates attached to each other. So this just shows a few examples. So this particular one is a constituent of honey. Some of these have pharmaceutical uses, so that's thought to have anti-cancer properties. For example, this one, we have the 6 carbohydrates in a ring, and we'll talk about that soon, maybe the next slide. Yeah, the next slide, where that has applications in chemistry lab. All right, so this is what's known as a cyclodextrin. So we have 6 carbohydrates in a ring. So they're derivatives of alpha D glucose. So it has applications in food industry, pharmaceutical industry, drug delivery. So you could potentially put a pharmaceutical agent here and then let the cyclodextrin deliver it somewhere within a cell. So there's kind of an interesting application of it if you've ever heard of alcohol. So the cyclodextrin has a fairly hydrophilic exterior because of the alcohols on it, and the interior is somewhat hydrophobic because of all of the carbon chains in the ring. So if you take this and you add ethanol to it, so if you make the cyclodextrin will dissolve in water or ethanol, and then if you take that and evaporate it off, then the ethanols will be trapped inside. So you could take ethanol, put some cyclodextrin in it, and then evaporate the alcohol and any water off, and so now you have a powdered form of alcohol. And so somebody who's going camping, for example, and didn't want to take a liquid with them could just pack in some powdered alcohol, and then when you get to the campsite you could take that and put it into water, and then the ethanols can, once it's in water, the ethanols can come out of the cyclodextrin and into the water, and then of course you can drink that. Cyclodextrin is safe to drink. It's just a sugar that could be metabolized, but that's a way to get powdered form of ethanol. So a lot of these, as I mentioned, a lot of the oligosaccharides are incorporated into pharmaceutical agents. So this just shows four different ones that have anti-tumor and antibiotic properties. So where are the sugars at in these molecules? So that's a disaccharide there, right? There's a disaccharide here. This is a sugar. Well, all of this is a sugar. Or in this molecule, all of this is a sugar, and all of this is a sugar. So they find important uses from pharmaceutical industry as well. Okay, so polysaccharides. So now if we're talking 10 to hundreds of carbohydrates linked together, so you can have homopolysaccharides, so that would just mean the same carbohydrate polymerized, or heteropolysaccharides, so you have different carbohydrates polymerized together. So they have many important uses. So starch and glycogen, which we'll talk about, are storage molecules, so energy storage. Chitin, cellulose, which we'll talk about, have important structural components. Polysaccharides could be on the surface of cells, which could be what's used for cell surface recognition. Okay, so what is starch? So it's just a polysaccharide. So it's basically a polymer of glucose. So two forms we'll talk about, amylose and amylopectin. So most starch is about 10 to 30% amylose and about 70 to 90% amylopectin. So we're talking 100 to 1,000 glucose molecules polymerized together. So what's the difference between them is that amylopectin has branches about every 25 glucose residues, and so they're and those branches are at the 1,4 glycosidic linkages. So amylose has 1,4 glycosidic linkages, and again typically 10 to 100 to 1,000 glucose residues long. So we'll look at the structures of them to make sure that makes sense. So this is just glucose molecules polymerized. To simplify the structure, we just haven't shown the OHs and Hs at those positions. But this will be the carbon number 1 of one glucose, right? And then carbon 1, 2, 3, 4 of another glucose. And it's an alpha 1,4 linkage, so the 1 and the 4 comes from here, right? Carbon 1 versus carbon 4. And why is it called an alpha linkage? So this oxygen is trans to that CH2OH. So we're talking about polymerizing alpha D-glucose. So alpha D-glucose, we have the structure shown here. So we're talking about polymerizing alpha D-glucose, where this OH, right, is on bottom of that H, and this CH2OH is on top of that H, so they're trans to each other, so that's the alpha isomer. So if you take that and polymerize that, then you have what's known as amylose. And okay, so then if we start branching it, so some of these, so this will be carbon 1, 2, 3, 4, what is that? Yeah, 5, and then this would be carbon number 6, and then this would be carbon number 1 of that carbohydrate. So this would then be a 1,6 glycosidic bond, and it's an alpha linkage again because that oxygen is trans to this CH2OH. So that would be a 1,6 glycosidic bond where the main carbohydrate chain has now been branched to make the amylopectin. Okay, so what is glycogen? It's just another polymer of glucose. So it's the main energy storage polysaccharide for animals. So it's about 10% of the mass of the liver, 1 to 2% of the mass of muscle. So it's an organism's main source of energy. So the only difference between starch and glycogen is that there's more branches. So more branches is going to make it more water soluble. And so an animal, of course, needs to have a more readily available source of energy than a plant would. And so the increased branches makes it a better source of energy. So, the more branches makes for more targets for enzymes to start hydrolyzing off glucose molecules, and then the glucose goes into metabolism to make ATP. So it's a source of energy for an organism. So glycogen then has alpha 1,6 linkages, just like amylopectin, but they're every 8 to 12 residues rather than about every 25 residues. And it's still a polymer of glucose with 1,4 linkages. So it may contain up to 50,000 glucose molecules. So this is just a big structure showing you the structure of glucose. So if we focus on right in here, just to illustrate, so that's carbon 1, 2, 3, 4, 5, 6, right? And this would be carbon 1 of the other carbohydrate, so that's a 1,6 glycosidic bond with an alpha linkage. So about every 8 residues, there would be a branch coming off of the main glucose polymer chain. Okay, so starch, amylose, amylopectin, and glycogen can be hydrolyzed by enzymes in both plants and animals, enzymes known as alpha and beta amylase. So the alpha and beta, in this case, don't signify the stereochemistry of the CH2OH and the OH of the hemiacetyl carbon. So what does beta amylase do? What does it do? So it's an exoglycosidase, so that means it cleaves from the non-reducing end of the polymer. So if you remember, the reducing end would be the end that's got the aldehyde or ketone on it. So this would be, so the non-reducing end would be cleaving it from this end, because at the reducing end, that through the process of muted rotation, right, the hemiacetal form can open up to make the aldehyde, but in this case, since that's a acetal bond, that cannot open up, so that carbon can't be oxidized by the oxidizing agents that we talked about in the last lecture. Since it's not a hemiacetal, it's an acetal or a glycosidic bond, so that's the non-reducing end of this carbohydrate polymer chain. So basically what the enzyme does is it comes in and it cleaves off two of these at a time. So that's what beta amylase does. Alpha amylase is an enzyme that can cleave at any glycosidic linkage anywhere. And then you have what are known as debranching enzymes, which can cleave the alpha-1,6 linkages. Okay, so here I have a graphic illustrating what is the non-reducing end of the carbohydrate polymer chain mean. So this would be the reducing end, this would be the non-reducing, no, this would be the non-reducing end. So it's not susceptible to oxidation. This is the reducing end, which is susceptible to oxidation because that is a hemiacetal, right? Whereas that is an acetal, right? That's a glycosidic bond linking two carbohydrates. This is a hemiacetal because it's got an OH on it, so that can open up, right, to do the process of muted rotation to give you the free alcohol and the free aldehyde, which can then be oxidized. So when beta amylase then starts digesting the glycogen or amylose or amylopectin, and then it cleaves off two carbohydrates from the non-reducing end at a time, and which gives the disaccharide maltose, which then gets further hydrolyzed to split that apart to give two molecules of glucose, which can then go into metabolism. Okay, so what is cellulose? So it is also a polymer of glucose. So it's the most abundant polymer on Earth. It's a structural component, right? It's what gives trees and plants their main principal structural strength. But it can also be soft and fuzzy. It's found in cotton. Right, so just some places that you find cellulose. So what's the difference between cellulose and amylose? So as we mentioned, amylose, amylopectin, glycogen have this alpha-1,4 linkage, whereas cellulose has a beta-1,4 linkage, right? So this and that are now cis to each other, right? Whereas here, that and the CH2OH are trans. So that makes a big difference because you can just see from this diagram there's kind of like a kink in the molecule here, whereas this is much more linear. And so cellulose then can form more fibro-like structures. Right, so that beta-1,4 linkage makes all the difference. It gives the molecule a more linear form, and so two molecules can get closer together, and then they can form stronger hydrogen bonds. So that interchain hydrogen bonding is what gives the structural aspect to cellulose. Another significance is that humans and other mammals, we have enzymes that can cleave alpha-1,4 glycosidic bonds, but don't have the enzymes that can cleave beta-1,4 glycosidic bonds, so we can't metabolize cellulose. Ruminants, such as cows and sheep, can metabolize cellulose though. How do they do this? Because they have bacteria in their digestive system that have the enzymes that can cleave the beta-1,4 glycosidic bonds. Okay, so what is chitin? So chitin is just a derivative of cellulose. where this is carbon 1 and carbon 2. So carbon 2 of these glucose, some of the glucose residues in the polymer chain have this N-acetyl functional group on it. So the significance of that is that, right, this H is very partial positive, that oxygen is very partial negative. So now these are available to form hydrogen bonds to other chains of this cellulose polymer, and so that'll give it a very even stronger structural component to it. All right, so that's cellulose. It's just a big polymer of glucose with beta-1,4 glycosidic bonds. Chitin is also glucose polymerized with beta-1,4 glycosidic bonds, but some of these two positions on the glucose residues have these N-acetyl groups on them, which allows for stronger hydrogen bonding interactions. Okay, so just a little diversion here, just to show you how some of this relates to just the real-world chemistry. So if you're paying any attention to nutrition, you probably have heard of high fructose corn syrup before. So what is high fructose corn syrup? So corn, so this corn starch, so just a polymer of glucose with these alpha-1,4 glycosidic bonds. And alpha amylase will cleave this up into smaller chunks. So now we just have, instead of hundreds to thousands of glucose, tens to hundreds of glucose, and then that can get further metabolized, glucose amylase, to break this polymer down into just glucose molecules. And then there's this enzyme that was discovered and patented in 1960 that will isomerize glucose to make some fructose out of it. So that enzyme will convert 100% glucose into a mixture of 42% glucose and 42% fructose and 58% glucose. And then through chromatography separation in lab, then you can enrich that to about 90 to 100% fructose. And then commercially what's done is to add some glucose back in to make high fructose corn syrup that's 55% fructose. And so what is this used for? It's used to sweeten soft drinks, for example. So the downside to this is that there's been some studies that suggest that high fructose corn syrup may be linked to obesity and diabetes. So why is it used? Well, because fructose is a lot cheaper than sucrose, right? So sucrose is what you would find in table sugar, right? Comes from plant sources such as sugar cane and sugar beets, which can account to 10 to 20% by mass of those plants' dry weight. Most fruits only have about 5 to 10% sucrose. Something like avocado has no sucrose at all. But anyway, sucrose is a lot more expensive than fructose, so that would be one reason why these companies that make soft drinks, for example, would rather sweeten their drinks with fructose than sucrose, because it's cheaper. All right, so there was an effort at one point, right, so the corn industry is highly subsidized by government. So there was an effort at one point to change the name of high fructose corn syrup to corn sugar, because I guess it sounded better, but the FDA rejected that. So here's another example of how these carbohydrates have been utilized, in this case the food industry. So this product called Oligosaccharides, or Olean. So basically what was done, so if you take glucose and fructose, then that makes sucrose. So you have lots of hydroxy groups here, right? And we've talked about reactions of alcohols and throughout the semester. So if you take an alcohol with acid chloride, so we talked about this in chapter 21, right? Then you can make an ester. So this is what's done, is to take sucrose and to use this long chain acid chloride to make these esters, to make esters out of all of these hydroxy groups. So, to simplify the drawing, I only showed 4 of them, but you could conceivably put an ester group at all of those OH, at all of those free alcohol positions. And then what this was used for is used as an artificial fat. It was a product developed by Procter & Gamble. They put it into some of their chips. I don't think the brand, I never noticed the brand on the shelf anymore, so maybe people were not too impressed with it. And there's reasons why maybe people were not too impressed with it. So there's some downsides to this, but as you can imagine, all of these basically fatty acid derivatives there, it kind of has the texture of fat, but it's not metabolized, so there's no calories to it. So the downside, so this would be something that was on the product label. So there's a couple of downsides. One, because it is a very hydrophobic molecule, right? I mean, you have all of these long alkyl chains in there. So it's a very hydrophobic molecule, and it can bind to hydrophobic molecules like vitamin A, vitamin D, beta carotene. Those are important vitamins, but they can get bound up in the olestra and then basically excreted, so you could end up with some vitamin deficiencies. But another downside to it was, well, you can read it here. Basically, it can cause diarrhea if you eat enough of it. So that's a pretty good downside to eating a whole bag of chips that have olestra in it. Okay, and then lastly, I just wanted to show a couple of other examples of where carbohydrates are important in biological chemistry. So these are nucleobases, right? Adenine, guanine, cytosine, thymine, which would be the nucleobases in DNA, or in RNA, then thymines replaced with uracil. The only difference being is a methyl group right there. Right? So if you take those and react them with 2-deoxyribose, so this is carbon 1, this is carbon 2, right? So 2 is missing a hydroxy, so this will be ribose, which has a hydroxy group there, so this will be 2-deoxyribose. So if you take those, and this is the hemiacetal carbon, and then link them, so instead of the OH there, the nucleobases are attached there. All right, so attach the nucleobases here. And then now you have the nucleobases attached to the ribose, or the deoxyribose. If it's RNA, then ribose. If it's DNA, then deoxyribose. So these are what are called nucleosides, where you have the nucleobase attached to the sugar. And then, of course, those can be phosphorylated. So you could phosphorylate it here. Or as we'll see, it's common to see it or you would if we're talking about growing a strand of RNA or DNA, then you're going to be phosphorylating it here. But if you can phosphorylate it there, and if you phosphorylate it there, then you have what are known as nucleotides. So this would be, so that's adenosine, so A, and then that's the monophosphate, right? So that would be adenosine monophosphate. Or you could put 2 phosphates there and have a diphosphate, or 3 phosphates there and you would have adenosine triphosphate. So of course the same for all of these different nucleobases. Attach them to the ribose and then phosphorylate them to get different nucleotide derivatives. Or for growing the RNA and DNA strand, then what would happen is you phosphorylate at this position instead. And so this would be carbon 1, carbon 2, and that's carbon 3 of that sugar. And for this sugar, carbon 1, 2, 3, 4, and that would be carbon 5. And so now if we link this, so if this oxygen is attached here and this is gone, and we basically polymerizing the molecule, then now that's how the DNA strand would grow. Or if this was an OH here, if this was ribose instead of deoxyribose, then that would be the RNA strand. All right, so obviously carbohydrates extremely important in biological chemistry. Okay, we'll stop there. So that's it for chapter 23. So the main thing to know in this chapter would be know the structural difference between like chitin and cellulose, where those 2 positions have these N-amide groups on them. Know the main structural difference between cellulose and amylose. So what the alpha 1,4 glycosidic linkage is versus the beta 1,4 glycosidic linkages, and the difference between amylose, amylopectin, and glycogen just being the number of branches. So along a main carbohydrate chain, then how many branches does it have, right? So that would be a branch. The glycogen branches about every 8 carbohydrates, for example. And then the other main thing to know here is knowing how to understanding this nomenclature, right? Understanding what alpha means, what the 1,4 linkage means, what the beta means, what the pyranose or furanose means, for example. Okay.